All right, today is the 19th of April, and we're going to continue our learning on waves. What is a wave? Wave is a disturbance in a medium, so it must be traveling through something, and it is transmitting energy from place to place. Here are some example of waves: ocean and light waves. It is important to distinguish between the motion of a wave and the motion of the individual particle. So we can have a graph that has the motion of a wave, which should have a distance, meter versus time in seconds, so we can see the wave traveling, as opposed to a graph of meters distance in the y direction and meters distance in the x direction. Okay, so it depends on the problem. You have to pay attention to what they tell you the graph is representing. In general, waves travel from place to place, but the particle of the wave oscillate back and forth about one location. They don't actually move. We've learned about two different types of waves: transverse and longitudinal. Transverse waves are the particle in the medium is traveling perpendicular to the wave motion or propagation. Longitudinal wave, the particle in the medium is parallel. Okay. We can see in this situation that we are traveling to the right, and the wave is traveling away from where it started from. And if I were to follow some particle here, it moves up and moves down. This is an example of a transverse wave. You can see the string, and here's like a piece of tape that's on the string, and that piece of tape is moving back and forth, just like we would in simple harmonic motion. So that particle is experiencing simple harmonic motion as the wave travels through it. Okay. Longitudinal waves, they are the particle is traveling parallel to the wave energy. And so here is an example. The wave is traveling to the right. We will have areas of compression and expansion. These areas of compression are considered high density areas, and these areas of expansion are considered this rarefaction, kind of a weird word, but that is the areas of expansion. Okay. A simple wave like the one shown in the figure below is a regular rhythmic disturbance. So this is a periodic wave, so it's happening over and over again. And these are something that we're going to have to work with. So this is the displacement of the wave as it travels. And we can see that we have some things. We have some crests and we have troughs, and we can measure the wavelength. This is meters. So this is how fast the distance or the wave as it travels in the x direction. If this is in meters, if I measure the distance from crest to crest, that will represent the wavelength. So this is one wave right here until it starts repeating again. So it's on the way down, and right here it's on the way down again. So if I measure crest to crest, I can measure the wavelength. I could also measure the wavelength if I measure the distance from trough to trough. Think about it this way: I'm on my way up, and now I'm on my way up. So this is one full length, and this is also the wavelength. The wavelength is given by the symbol gamma, and is measured in meters. So the highest points on the waves are called crests. The lowest points are troughs. The wave repeats itself over and over, equal, and the distance is equal to the wavelength and the distance between the consecutive crests or troughs. So you could measure the wavelength either from the distance from the crest to crest or trough to trough. Okay, some other things that we know now. We know the amplitude, which is the distance from the wave's equilibrium position to its maximum displacement. We've learned about period, and we know that that would be the time it takes for a wave to move one wavelength. So we need to take a look at that again. So as it moves, the time it takes for this spot of energy to move to this spot is 1 cycle, so that would be its period. We can also, if we know the period, right, we had find the frequency. A lot of times, actually, we talk in terms of frequency with regards to waves. So we will inverse period to get the frequency, and we will get to our equation here. So the speed is the distance the wave travels, which is its wavelength, divided by time, which is that period, and that is its speed. Okay, so here is that equation. However, the one that we see the most in physics is, instead of putting gamma over period, we have the frequency is equal to the I'm sorry, the velocity is equal, or the speed is equal to the frequency times the wavelength. Okay, so this is the key equation for waves. Okay, this is this equation applies to all waves, no matter what their type or how they are produced. So let's go ahead and find some, do an example. We have sound waves that travel in air with a speed of 343 meters per second. The frequency of the lowest sound that you can hear is 20 hertz. And the frequency of the highest sound you can hear is 20 kilohertz. This is the lowest. This is kilohertz, is the highest. Okay, find the wavelengths of sound waves having frequency of 20 and 20 kilohertz. Okay, so we'll say we want to know the wavelength, and we know that the speed is equal to the frequency times the wavelength. So we'll rearrange that for the wavelength, which will be speed over frequency. And so in the first case, it is 343 meters per second over 20. And hertz is cycles per second. So the seconds will cancel, and that will give me 343 divided by 20. And that is a wavelength of 17.5 meters. The second one is, we're going to follow the same procedure. We will find the wavelength. In this case, it's 343 divided by 20 kilohertz. Well, kilo is 1,000. So 1 kilohertz is equal to 1,000 hertz. So now I've converted that to hertz. And so I take 343, divide by 20, divide by 1,000. Oops, I did something wrong. 343 divided by 20 divided by 1,000. And that will give me a wavelength of 0.0172 meters. So that's a pretty substantial difference in wavelengths between the frequencies that we can hear with our ear. Okay. Waves travel with different speeds in different materials. Okay, so the speed of the wave, this is important in AP Physics, is dependent on the medium in which it travels. So speed of sound in air is 343. That's temperature dependent, by the way, as temperature changes can affect that speed. That has to do with the density of the particles. Water sound is 1,400 meters per second, so much faster in a more dense material. And solid steel, sound travels through solid steel even faster yet, even more dense. Temperature, again, can make a difference because sound travels faster in warmer air than it does in cooler air. All right, that's what I got for you today, and we will complete our homework packet.